Okay, so in this section, we are looking at improper integrals. So what makes an integral improper? Well, there are a couple things. It could be over a finite interval, or it could be semi-infinite. It could be a closed interval where there's an infinite discontinuity somewhere inside AB. And we're also going to learn the comparison theorem to see whether or not an integral is convergent. Okay, so, oh, I did want to make a comment. So when we took the exam, oh, nope, never mind. Never mind, I'm going to keep going. Okay, so here are examples. Oh no, please don't do this to me. Okay, it's good. All right, so here are some examples of improper integrals. This one is actually supposed to say the integral from a to infinity. That's supposed to be an infinity. Okay, so again, it starts at a, it goes to infinity. You can't, when you're doing the evaluation, you can't just stick infinity in there like we do a definite integral. Same thing for the integral, pardon me, from minus b to minus infinity to b, and then from minus infinity to infinity. We also have some type of integrals. If you notice this integral, which goes from 0 to 5 of 1 over the square root of x dx. Can anybody give me an idea of what they think might be wrong with this integral? What might be wrong with this integral? Anybody have an idea? Okay. All right, so this integral is improper because notice that I have 1 over the square root of x, but this here has 0 as the limit. And so 1 over the square root of x is not even defined at 0. So how do you do this integral? So we're going to do one or two of those. Okay, so here's the main thing. That is, how do we define convergence? Okay, so let's define convergence of an integral. So convergence means we're usually trying to reach a particular point. If you converge at an intersection, the two of somebody will meet at an intersection. So convergence means we kind of tend to go to something. So an improper integral is said to converge if you can take the integral from a to infinity, and this also goes for the other two cases that I have. And when you integrate it, you get a number. It doesn't matter what the number is, as long as you get a number and not infinity, the integral converges. If when you do the improper integral and you get infinity, then you know the integral diverges, which means the area underneath the curve going toward infinity or minus infinity keeps going to a level that it's always increasing. It can never converge to a finite number. Okay, so how do you compute this? Your book uses t, so I'm going to use t. So the integral from a to infinity of a function f of x, you have to put a t in for infinity, evaluate the integral, and then when you're done, take the limit as t goes to infinity. If that gives you a number, then it converges, okay? Hang on just 1 second. Let's keep going. Okay. Also, if it's an integral that's infinite on the left end, so it goes to minus infinity, then again, I'm going to let t, and this should go to minus infinity. There we go. So the limit as t goes to minus infinity. And so that would make this, I evaluate this part of the limit. So I'm going to evaluate the whole integral. And then at the end, I will take the limit. Okay, so I hope you guys are really up to snuff on your limits. Okay, so here's the first problem. Find the area under the curve of the function f of x equals 1 over x on the interval 1 infinity. All right, so what does that look like? Okay, so at 1, this thing is 1.
Okay.
And then it decreases.
Fine.
And it keeps
Okay.
decreasing.
Okay, let me see what.
And so as it keeps decreasing, we're trying to find the area under this curve. And notice the area continues to go, it keeps going and it goes all the way out to infinity. So we want to find the area under this curve as it goes out to infinity. Okay. All right, so we want to compute that. Okay, that doesn't seem difficult. Uh-oh, let me move this problem. Move this guy. I said move this guy. Okay. So I want the integral from 1 to infinity of 1 over x dx. All right. So if I take this, I'm going to rewrite it as the limit as t goes to infinity of the integral from 1 to b. So in the place of infinity, I'm going to have that of 1 over x dx. So now this is the limit as t approaches infinity. And then this integral right here, 1 to b of 1 over x, what happens when I integrate that? What do I get? I have 12 people on here, which is not great because there are about 20 people in the class, at least. So I have 12 people on here. I need one of you, just one person to give me the integral of 1 over x dx. What is it? Come on.
Ln of x.
What did you say?
Ln of x.
Okay, so the natural log of the absolute value of x, we're still going to stick that in there. Evaluate it from 1 to b. Now I already know b is going to infinity, so I know that b is positive, so I'm going to drop the absolute value. So when I do this, this is the natural log, so I get the limit as t approaches infinity of the natural log of t minus the natural log of 1. Now we already know the natural log of 1 is 0. So this is equal to the limit as t approaches infinity of the natural log of t. And what happens? As t goes to infinity, what happens to the log of t? It goes to what? The log of t goes to, oh, that's scary. Alexis, what does this go to as t goes to infinity? What does the log function do?
I'm honestly not sure.
Okay, so let's look at the log function. Let's go back. Thank you for that, because you're not the only one who's not sure. Oh my goodness. You're just only one willing to say so. Okay, so here's the logarithm function. The logarithm function looks like this. Okay, it goes to infinity as t goes to infinity. So if this is t, and this is y equal to the natural log of t, it's going to infinity. So this limit goes to infinity. So that is not a number, it's infinity. So this integral diverges. Okay. Now I had another example to do. Maybe I'll do the other example first, and then I like this example, so we'll slide this in somewhere. I'm not sure where. Okay. Fun, fun, fun. Okay, next problem. So now we want to find the volume of the solid. Ooh, that's a throwback, isn't it? Generated by revolving that same curve above about the x-axis on the interval from 1 to infinity. So let me move this guy. So the only thing that we're going to do differently now is we're going to take this same picture. And we are going to revolve it about the x-axis. Okay, so when we revolve it about the x-axis, if you remember, we choose a point. And we're going to revolve it. So we're going to end up with something that looks like this. Okay. All right, so this thing is revolved. So what technique am I going to use to revolve this about the x-axis? What do you see? You've had plenty of time to think. What method am I going to use? So we learned several methods back a while back about revolving things about axes. What method am I going to use?
Is this the disk method?
That is the disk method. Okay, so we will use the disk method. All right, so if we remember the volume, the integral from a to b of pi times the radius squared dx. All right, so for us, the radius, if I drop a radius right here, I can see my radius is simply just my height, which is f of x, or 1 over x. Okay, so now I get that the volume is the integral from 1 to infinity, because this thing doesn't stop, of pi. The radius is 1 over x squared dx. So now that's going to be the limit as t approaches infinity of the integral from 1 to t of pi. And then I have 1 over x squared, which I can write as x to the negative 1. I'm sorry, x to the negative 2 dx. All right, any questions so far about what I just did? So here I had 1 over x squared. I just rewrote it as x to the -2. All right, so that's an easy integral. This is the limit as t goes to infinity. I have minus pi x to the -1 evaluated from 1 to t. So that's the limit as t approaches infinity. I have negative pi. And then I'm going to get t to the -1, which is 1 over t. And I'm going to get 1 to the -1, which is 1. Okay, so somebody tell me something. What happens as t goes to infinity? Good, 1 over t goes to 0. So since 1 over t goes to 0, this just becomes minus pi times -1, which is pi. And how wonderful is that? That's a number that is less than infinity. So this interval converges. Integral converges. Okay. Any questions about that? Okay, problem 3. All right, so this one is going to, I like the fact that now we're using everything that we learned. So as somebody, one of my colleagues said, math is a chain. You have to know the beginning of the link in order to get to the end of the link. Okay, so we want to compute this integral. All right, so this is the integral. This is the limit as t approaches negative infinity. The integral from t to 0 of dx over x squared plus 4. Okay, so the only thing we need to do now is integrate dx over x squared plus 4. What does that give us? Dx over x squared plus 4. What does that give us? What is that integral? You guys know that integral. Okay. Tremont, what's the integral of dx over x squared plus 4? This is one of the ones that we learned. Tremont, are you there? Anybody?
Would you use tangent inverse?
It's the tan inverse. Okay, so thank you for helping him. So this is 1 over 2, the tan inverse of x over 2 evaluated from t to 0. So this is the limit as t approaches infinity of 1/2. I'm going to get the tan inverse of 0 minus the tan inverse of t over 2.
I have a question.
Yes.
Why we change from negative to positive?
Why did what?
The infinity.
Because it should be negative infinity. Now it's correct. Now it is correct. Okay, does anybody know how to work with this? So let's say I call this I don't want to call it I. Let's just say I call it Y1. And I'm going to call this Y2. Okay, so the first one does not have a T in it at all, no T. So the first one is Y1 is equal to the tan inverse of 0. So that says the tangent of Y1 is equal to 0. So what is Y1? Y1, what is the angle whose tangent is 0? What is Y1? Hello? Anybody? Are y'all even here today? Okay. Here's the tangent. This is the tangent function. Okay, this is negative pi over 2. Here is pi over 2. So the angle whose tangent is 0 is 0. So Y1 is 0. Okay, that's good. Now we got to do Y2. Y2 is the limit as t approaches negative infinity. I'm not even going to worry about the 1/2 or the negative. I'm just going to worry about the tangent. So Y1 here, let's do Y1. Y1 is the tan inverse of t over 2. So that says the tangent of Y1 is equal to t over 2, or 2 times the tangent of Y1 is t. All right. So now I'm taking the limit of that. Actually, I'm going to leave my 2 right where it was. So the limit as t goes to infinity, negative infinity, of the tangent of Y1 is t over 2. So this goes to negative infinity. So if that's going to negative infinity, then Y1 has to be negative pi over 2. Because that, as you can see, is going to negative infinity. Okay. So now if I go back to my problem, this is equal to the limit as t approaches negative infinity. Oh, actually, we already did that. We already know what everything is. So I'm just going to put in 1/2 We got 0, and then we got minus a negative pi over 2. So the answer is pi over 4.
Unknown caller.
So this converges. Okay. I know that one's a little tough. All righty. Let's compute this next one. Okay, so here's one from negative infinity to positive infinity. All right. So we could split this up into two separate integrals. Since everything is okay inside the integral, we could split it up into two separate integrals, or we could do the limit as t approaches infinity of the integral, and now I'm going to put t up here and negative t down here, of x e to the negative x dx. Okay, so how do I do this integral? This inside integral here, how do I do this integral? What is the technique? We learned 4 major techniques in the last section. Actually in the last module. How do I compute this integral?
Integration by parts.
Okay, integration by parts. Awesome. Okay, so I'm going to do the easy way. I'm going to do the tree. So I have the derivative on this side and the integrals on that side. So I get x, the derivative of x is 1, the derivative of 1 is 0. I get e to the negative x. The integration of that is negative e to the negative x. The integration of that is e to the negative x. I know that I'm going to link them like this. And I also know this one is positive and this one is negative. Okay, so I'm good. So this is the limit as t approaches infinity. Okay, and so therefore I get, when I integrate this, I'm going to get negative x e to the negative x minus e to the negative x evaluated from negative t to t. All right, so this is the limit as t approaches infinity. So I'm going to factor out the e to the negative x and make this times x plus 1 evaluated from negative t to t. Okay, so now let's do the first piece. So we get the limit as t approaches infinity. So the first one is going to give us negative e to the negative t times t plus 1. And then we're going to subtract off the second one, which is going to give us e to the t times t plus 1. And so now how do I evaluate this? Okay, so I need to evaluate the limit. So again, the limit of these things. So the limit of this piece and the limit of this piece. All right, so the first one is the limit as t approaches infinity of e to the negative t, puts a t plus 1 at the top and an e to the negative t at the bottom. I'm sorry, e to the positive t at the bottom. And this is equal to infinity over infinity. Oh, that's wonderful. What rule can I use? What rule can I use?
L'Hopital's rule.
L'Hopital's rule. Awesome. All right, so therefore this is going to equal the limit as t approaches infinity. And so now I'm going to get 1 over e to the t. And as e to the t, as t goes to infinity, e to the t goes to infinity. So 1 over that is 0. Yay, the first term goes to 0. We're all good. This term goes to 0. How about the second one? We get the limit as t approaches infinity of e to the t times t plus 1. Well, that looks like infinity times infinity, which is still infinity. Oh, that's a problem. That's a problem because the second term goes to infinity. So that means this thing goes to the limit in the end when we're done. This thing is actually equal to infinity. So this is going to diverge. Okay. So we've seen some converge and we've seen some diverge. All righty, the comparison theorem. So we're going to do the first part. Okay, so suppose we have something we really can't integrate. But we still need to determine whether it's convergent or divergent. So we can compare it to a function that's either larger than it or smaller than it. So if we have f of x is less than g of x on the interval a infinity, this also works on the interval minus an integral minus infinity b, and it also works on the whole thing minus infinity to infinity. Okay, so if this integral, if f of x is less than g of x, and the integral from a to infinity is convergent, so this means this integral converges. See, it is less than infinity, so this integral is convergent. Then the integral from a to infinity, which is smaller than the integral from a to infinity of g, which we said equaled L, forces f of x to be convergent. All right, so now f of x converges. Okay, any question about that? So here it is written for the bottom. Okay, so if f of x is less than g of x, this time we're on the interval minus infinity to some b. And the integral from minus infinity to b of g of x is equal to L, so this thing is convergent. Then since f of x is less than g of x, its integral will be less than the integral of g of x. So f of x converges as well. Okay, any questions on those two? Okay. Here's the other part of the theorem. If f of x is still less than g of x, so we still have the function one smaller than the other. Oh, now the integral from a to infinity of f of x blows up. All right, so this integral diverges. Then the integral which is bigger than it, which I didn't write, I guess I should have. Yeah, I'll just write it like that. Then the bigger integral also is going to go to infinity. So g of x is going to diverge as well. Okay. And of course, we get the same thing for the integral from minus infinity to b. So if f of x is less than g of x and f of x diverges, then g of x will diverge as well. Okay, so let's use the comparison theorem. I think this might be the last thing we get through today. Oh, that is definitely not what I want. I want to do this integral. Okay, so let's compute this integral. Now, I already know we just did an integral similar to this, and we got tan inverse. Okay. But I know that this integral, because I have x squared plus 4, I know that f of x, f of x is 1 over x squared plus 4, which is less than g of x, which is 1 over x squared. So I'm going to try to compare these integrals. So f of x is indeed less than g of x. So if g of x converges, I'll know f of x converges. Okay. All right, so let's look at g of x. So the integral from minus infinity to 1 of 1 over x squared dx is the limit as t approaches negative infinity of the integral from t to 1 of x to the negative 1 next to the negative 2 dx. Okay, well, that's the limit as t approaches negative infinity. I know this is negative 1 over x evaluated between t and 1. So that's the limit as t approaches negative infinity. I'm going to get negative 1 over x plus 1 over t. And we said as t goes to infinity, or negative infinity for that matter, this will go to 0. So this integral goes to -1. Yay, that is a finite number. So this integral converges. So that implies our original integral also converges because it was smaller than something that converged. Okay, so that is the comparison theorem. Any questions about that? So if you can make it bigger than something that diverges or smaller than something that converges, then you can use the comparison theorem. Okay, we still have 4 minutes, so I'm going to do this one last section. So what's the case where the integrand is not continuous? So some of these will work and some of these will not. Okay. So this is one, like I said in the beginning, where the integrand is not continuous at one of the boundary points or the endpoints. So the square root of x is not continuous at x equals 0. Note 1 over the square root of x is not continuous at x equals 0. So we're going to take this integral and write it as the limit as t goes to 0, not infinity, but 0 of the integral from t to 4. And then this looks like x to the -1/2 to me dx. So that's the limit as t goes to 0. I'm going to get add 1/2. So I'm going to get x to the 1/2 and multiply it by 2, evaluate it between t and 4. So this is the limit as t approaches 0. I'm going to get 2. The first one, I'm going to get the square root of 4 minus the square root of t. And as t goes to 0, this goes to 0. So I just get 2 times 2. So that's 4. So this interval is convergent. Okay, any questions about that? Comments about this? Does this seem easy or more difficult?
Definitely difficult.
Okay, what's difficult about it?
Like, I feel like I'm trying to follow. I really am. It's just, I get one part, then the next part is just like, what happens?
So where did
I
I
feel like
lose you? Tell me where I lost you.
Just with this problem or the whole thing?
Either one, whatever you want to tell me. Oh, I didn't take attendance. Dagnammit. Let me do it real quick while you think of what your answer is. I'm going to take attendance. Let's see, somebody is. Thank you, Mikhail, and I'm going to fix your attendance right now.